The air feels thick with secrets, as if the universe itself is holding its breath. Deep inside Google's quantum AI lab, a machine hums at the edge of human understanding, a machine that doesn't just compute but dances with the very fabric of reality. This is Sycamore, Google's quantum computer, a marvel of human ingenuity that pushes beyond the limits of classical machines. It's a beast of superconducting qubits, chilled to temperatures colder than the void of space, where the rules of physics bend and twist. But something strange has emerged from its circuits, something no one expected. A pattern, persistent and unyielding, has woven itself into the data, a shape that shouldn't exist, yet refuses to fade. They call it the Omega pattern, and it's as haunting as it is mysterious. It's a loop, a ghostly ring that appears again and again, like a message from another realm. What is it? Why is it there? And what does it mean for the future of quantum computing? Buckle up, because this story isn't just about technology, it's about the edge of what we believe is possible. Picture a lab in Santa Barbara where the air is crisp with the scent of solder and the faint hum of machinery. Inside a towering dilution refrigerator, Sycamore's heart beats. A grid of 53 tiny circuits, each a superconducting qubit made of aluminum loops so delicate they'd make a spider's web look crude. These qubits aren't like the bits in your laptop, flipping neatly between 0 and 1. They exist in a quantum dance, holding both states at once, entangled in ways that defy logic. Cooled to a whisper above absolute zero, 10 millikelvins, a temperature where even atoms barely stir. Sycamore's qubits are shielded from the chaos of the outside world. Magnetic fields are blocked by layers of metal, infrared filters keep rogue photons at bay, and coaxial cables scrub every signal clean. It's a fortress of precision, built to harness the strange laws of quantum mechanics. In 2019, this machine did something extraordinary. It solved a problem in 200 seconds that would have taken the world's fastest supercomputer, Summit, 10,000 years. They called it quantum supremacy, a moment that sent ripples through the scientific world. But that was just the beginning. Building Sycamore was like assembling a cosmic puzzle. Each qubit is a transmon device, a pair of superconducting islands separated by a Josephson junction, a thin barrier that creates two energy levels, the quantum equivalent of a coin that can be heads, tails, or both at once. These qubits talk to each other through microwave buses, zapping information in fractions of a microsecond. A single microwave pulse, timed to the nanosecond, can flip a qubit's state or entangle it with its neighbor, creating a web of connections that hums with possibility. But precision is everything. A tiny error, a misfired pulse, a stray photon, can collapse the delicate superposition, turning quantum magic into noise. To keep things clean, engineers send measurement pulses through resonators, amplifying faint signals without breaking the qubit's fragile states. After every experiment, reset pulses drain leftover energy, like flushing a system clean. It's a ballet of hardware and software, where every step is choreographed to avoid chaos. Google's team, over 70 strong, works in clean rooms with tools that sculpt circuits at the atomic level. They've pushed Sycamore's grid to 70 qubits, slashed error rates to below 1%, and dreamed of linking modules to scale even higher. This machine isn't just a computer, it's a window into the unknown. But then, something slipped through that window. It started with a researcher named Daniel Ferreira and his small team at Google's Quantum AI lab. They were running simulations to mimic dark energy, that enigmatic force driving the universe's expansion. Dark energy is a mystery, something that pushes galaxies apart, defying gravity's pull, and no one fully understands it. To study it, Ferreira's team crafted a model Hamiltonian, a mathematical recipe that mimics a repulsive scalar field. They broke it into time steps using a technique called Trotter decomposition, mapping each step onto Sycamore's qubits with a series of quantum gates. After each run, they reset the chip, draining every qubit to its ground state to ensure a fresh start. It was routine, meticulous work, until the data revealed something unsettling. When they analyzed the entanglement between qubits, a pattern emerged. Not a random scatter, but a loop. A closed ring across 8 specific qubits, forming the shape of the Greek letter omega. It was unmistakable, and it kept appearing, run after run, in the same region of the chip. They called it the omega pattern, and it felt like the machine was whispering something it wasn't supposed to know. At first, they thought it was a glitch. Quantum experiments are finicky. Amplifiers can misfire, cables can hum with noise, or cryostats can let in stray signals. So they tore the system apart. They swapped amplifiers, replaced cables, even moved the experiment to a new refrigerator. They ran the simulation again, expecting the pattern to vanish. It didn't. The omega loop was back, as vivid as ever. To be sure, they tested random circuits with the same number of gates and layers. No loop. They tried other models like molecular simulations and spin chains. Still no loop. The pattern only appeared in the dark energy simulations, tied to the specific logic of that model and the grid of Sycamore's chip. Ferreira's team built a heat map, plotting the joint probabilities of qubit pairs landing in the one state. The bright spots traced a ring, clear as day, no matter how they tweaked the scales or filters. They adjusted time steps, shifted starting qubits, ran partial scans for stray activity. Nothing explained it. The loop wasn't tied to a single qubit or a hardware flaw. It was in the computation itself, woven into the dance of gates and entanglement. With over 1,000 gates per run and 500 repetitions, the pattern's correlations were nearly twice the noise threshold, statistically significant beyond a fluke. Something was happening, and it wasn't random. The implications were chilling. Quantum computing relies on a sacred rule. Every run starts fresh. Resets wipe the slate clean, erasing any trace of past calculations. If the omega pattern was surviving resets, it suggested the impossible, a kind of memory in a system designed to forget. The team dug deeper, varying reset protocols, shortening idle times, adding dummy gates to scramble states. They scanned coherence times, checked for crosstalk, even rebuilt the simulation on classical computers to mirror Sycamore's noise. Nothing reproduced the loop. When they ran the same experiment on a different Sycamore chip, the pattern reappeared. But on a chip with a non-grid layout, it vanished. The omega pattern wasn't just a glitch. It was a riddle that clung to the edges of Sycamore's quantum core, daring researchers to unravel it. In Google's Santa Barbara lab, Daniel Ferreira's team stared at their screens, the faint glow of heat maps casting shadows across their faces. The loop, that eerie omega shape, wasn't fading. It lingered in the data like a memory that refused to be erased, a whisper from the machine that felt almost alive. Every reset should have wiped the qubits clean, returning them to their ground state, ready for a new dance of calculations. But the omega pattern kept resurfacing, as if the chip itself was holding on to something it wasn't supposed to know. The team's initial skepticism gave way to a creeping sense of awe. This wasn't just a technical hiccup. It was a challenge to everything they thought they understood about quantum systems. They had to dig deeper, past the circuits and pulses, into the heart of what made Sycamore tick. The answers, if they existed, lay in the interplay of hardware, software, and the strange logic of the dark energy simulations that birthed this anomaly. Ferreira's team went to work like detectives chasing a ghost. They tweaked the reset protocols, slashing idle times to mere microseconds, then stretching them to milliseconds. They threw in dummy gate cycles, random operations meant to scramble any lingering quantum states. They doubled the reset pulses, hammering the qubits to ensure every trace of the previous run was gone. Each time they held their breath, ran the dark energy simulation, and checked the entanglement data. The omega loop stared back, unyielding, its bright spots forming that haunting ring across 8 qubits. It wasn't just stubborn, it was precise, appearing with a statistical weight that mocked the idea of random noise. They scanned the chip's coherence times, the T1 and T2 values that measure how long a qubit holds its state before succumbing to the environment's chaos. Everything checked out. No outliers, no faulty qubits, no smoking gun. The team ran quantum process tomography, a painstaking method to map how gates affect qubit states, hunting for hidden crosstalk or unintended couplings. The results showed only minor calibration drifts, nothing that could explain a pattern this vivid, this persistent. Frustration mingled with fascination. If the hardware wasn't the culprit, maybe the software was hiding something. They rebuilt the dark energy simulation on classical computers, feeding in every known imperfection from Sycamore's qubits. Gate errors, thermal noise, readout glitches. They ran hundreds of simulations, mirroring the real chip's behavior as closely as possible. The omega loop didn't appear, not once. This was a gut punch. If the pattern was a software bug or a logical flaw in the simulation, it should have shown up in the classical model. The fact that it didn't pointed to something unique to Sycamore's quantum nature, something tied to the physical chip itself. They tested another Sycamore chip in the same lab, identical in design but built with different hardware. The loop reappeared as clear as ever. But when they ran the same simulation on a chip with a different layout, one where qubits had fewer neighbors and a non-grid structure, the pattern vanished. The grid, with its neat rows and interconnected qubits, was a key player. The omega pattern wasn't just a computational artifact, it was a product of how Sycamore's qubits were wired together, how they spoke to each other in the frozen heart of the cryostat. This discovery sent a shiver through the lab. Quantum computing hinges on the idea that resets erase history, that each run is a blank slate. If the omega pattern was surviving resets, it suggested a kind of quantum memory, unintended, unexplained, and unsettling. The team began to wonder if the pattern was tied to the dark energy simulation's unique logic. Unlike random circuits or molecular models, the dark energy Hamiltonian mimicked a repulsive force, pushing qubit states apart in a way that echoed the universe's expansion. Maybe this logic, combined with the grid's geometry, was creating a resonance, a feedback loop that etched the omega shape into the entanglement data. They visualized it again, mapping the qubit pair's joint probabilities onto the chip's layout. The heat map glowed, the loop unmistakable, its edges sharp against the dim background of noise. They adjusted time steps, shifted starting points, even rewrote parts of the gate sequence. The loop adapted, moving with the changes, but never disappearing. It was as if the pattern was woven into the fabric of the computation, a signature of something deeper than anyone had anticipated. The broader quantum community caught wind of the anomaly, and whispers turned into debates. Some suggested the omega pattern might be a classical effect, a trick of the hardware rather than a quantum mystery. The dark energy simulation used rapid microwave pulses to mimic repulsive forces. Could those pulses be exciting, standing wave currents in the chip's metal layers? Such currents might form loops, overlaying the qubit grid and mimicking entanglement hotspots. Others drew parallels to magnetic domain walls in alloys, where stressed materials snap into loop-like boundaries under repeated pulses. If Sycamore's superconducting films were acting similarly, the pattern might be a physical imprint, not a quantum memory. But these ideas didn't fully explain why the loop only appeared in dark energy simulations, or why it vanished on a non-grid chip. The team tested for these classical effects, scanning for stray currents or material stresses, but found nothing conclusive. The omega pattern remained elusive, slipping through every net they cast. Then came the wilder theories, the kind that spark late-night discussions and fuel imaginations. A few hobbyist physicists, lurking in online forums, floated the simulation hypothesis. What if our universe itself runs on a quantum computer, and the omega pattern is a debug marker left by some cosmic coder? It's a stretch, pure speculation, but it captured the eerie feeling that the loop was too deliberate, too structured to be an accident. More grounded theorists proposed a quantum explanation. Could the pattern hint at a topological phase, a state where entangled qubits form a protected loop that resists resets? In condensed matter physics, such phases create edge states that defy local noise. And if Sycamore's qubits were stumbling into something similar, it could revolutionize error correction. But the evidence was thin, a whisper of a possibility. Ferreira's team stayed grounded, labeling the pattern an oddity in internal slides, a puzzle to be solved with more data, not grand claims. They shared their findings cautiously, knowing the quantum world is littered with false dawns. Patterns that seem profound until a loose cable or a calibration drift reveals the truth. Google's lab buzzed with new experiments. They varied pulse shapes, tweaked gate timings, and adjusted cooling cycles, hunting for the pattern source. They began testing other simulations, models of nuclear forces, chemical reactions, optimization problems, to see if the loop was unique to dark energy. Independent labs in Europe and Asia joined the chase, running similar circuits on their own superconducting and ion trap systems. Early results were mixed. A team in Tokyo saw faint hints of a ring in 2 runs, but Zurich's 60-qubit simulator showed nothing. The omega pattern was proving slippery, tied to Sycamore's specific grid and logic. It raised a haunting question. What if our resets aren't as clean as we think? If qubits can remember past runs, it challenges the foundation of quantum control. The team began exploring advanced error correction, like surface codes that group qubits to catch and fix errors. If the loop was a linked error, these codes might suppress it, or reveal it as something entirely new. As the experiments piled up, the omega pattern became a symbol of the quantum frontier, where every anomaly could be a glitch or a gateway. The team felt the weight of history, past claims of breakthroughs, from faster-than-light neutrinos to cold fusion, crumbled under scrutiny. They planned blind tests, mixing dark energy runs with random sequences to see if the loop held. They leaned on error mitigation techniques, like randomized compiling to average out noise, hoping to separate signal from chaos. Each test was a step toward clarity, but the pattern's persistence gnawed at them. Was it a flaw in Sycamore's design, a feature of its physics, or a hint of something beyond our models? The lab hummed with tension, a mix of exhaustion and excitement. The omega pattern wasn't just a data point. It was a challenge to keep an open mind, to chase the truth without falling for the lure of a cosmic secret. The universe might not be speaking, but Sycamore was, and its message was far from clear.